たします。皆さん、こんにちは。はじめまして。私はズフォンチェンです。
私はインイチェンです。
どうぞよろしく。はじめまして。
Good afternoon, everyone. We come from Taiwan, Pingtung country, Fang Liao Senior High School. The topic of our study is the synthesis of nanostructured AUPD catalysts for enzyme electro-oxidation reaction. Our work is to investigate how to improve the efficiency on enzyme electro-oxidation reaction with AUPD catalysts in different nanostructures. Direct alcohol fuel cells have been attracted great attention on their potential application in the portable electronics. Direct alcohol fuel cells relies upon the oxidation of alcohol on the catalyst layer to form carbon dioxide. Water is consumed at the anode and is produced at the cathode. Protons are transported through the proton exchange membrane to the cathode, where they react with oxygen to produce water. Electrons are transported through an external circuit from anode to cathode, converting chemical energy into electrical energy efficiently.
Among various liquid fuels, the methanol and ethanol have been recognized as the widely used fuel. Why are we introducing direct ethanol fuel cells? In contrast with methanol, ethanol generates a higher energy density, around 8,000 watt-hours per kilogram. Besides, ethanol is also attractive as inexpensive, renewable, non-toxic, stable, sustainable, and readily available. Furthermore, ethanol also can be obtained in great quantity from biomass through a fermentation process from the renewable resources, like from sugarcane, corn, wheat, or even straw. Why did we choose gold and palladium? There are two reasons. First, PD is a good catalyst on ethanol oxidation, contrast with PT. PD is more abundant, less expensive, and difficult to be poisoned by intermediate CO. Second, AU is expensive, but most literature confirms that it can not only enhance the catalytic stability and activity, but also further improve the CO poison problem on PD. So we combine AU and PD in our study. The research purpose of our study are as follows. First, synthesis of AUPD nanocatalysts. In the beginning, we use one-part compound to synthesize the nanoparticles. Second, investigating the relationship between the nanostructure of AUPD nanocatalysts from different synthesis conditions. In the study, we mix two different surfactants in the synthesis to study the structural change. Moreover, we tune the ratios of AU and PD to find out the best composition of catalyst. Third, electrochemical ethanol oxidation by the use of AUPD nanocatalysts. In order to check the activities and durabilities of our catalyst, today I will introduce the process of synthesis for you, and my friend will explain the data of ethanol oxidation. This is the setup to synthesize the nanoparticles. We synthesize the nanoregular icosahedral in our study. In the experiments, we use sodium citrate to reduce the metal ion AU and PD and affected the structure of catalyst under the condition of halide ion in 90 degrees Celsius for 16 hours. This is the sample we got. After synthesizing, we can get this picture. We can find our particles are uniform. In this experiment, we mix two different surfactants and change the ratios. We can find the structure of catalyst changes from LA to kosher since the high content of bromide to high content of chloride. The evidence is here. This picture shows the elemental distribution scanned and analyzed by EDES in left to right order. The red part is AU while the green one is PD. In the LA case, we can see the AU and PD grow and be well mixed. As for the kosher case, we can see the AU from the core and PD from its shell. So we can always see more PD sign around the color than in the middle. In addition to the experiments, we also change the ratios of AU and PD in LA and kosher case. We can find the LA structure remain in different composition. However, in the kosher structure, the PD share will increase with increasing PD content. Why are the structure of catalysts different? This is their formation mechanism. Because in the ratio of high content of bromide, their reduction rate is close and their reduction rate is lower, so we can get the LA structure. However, in the ratio of high content of chloride, the AU reduction rate is much faster than PD, so we got the AU chlor and PD shell. Then we synthesize the LA and kosher structure in different ratios of AU and PD to perform the enzyme electrochemical oxidation.
After synthesize the catalyst, we did the enzyme oxidation. But before that, we have to know the ECSA, electrochemical active surface area, so we did the CO stripping. This figure shows two curves. The black curve is the first scan after CO adsorption, and the red curve is the scan after the black one. We can see the peak is disappeared, and it demonstrated the CO stripping is successful in this way. To calculate the ECSA of all the catalysts, we integrate the peak area and divide by the scan rates. Then we can get this number, which is the total charge to remove all the CO molecules. And we knew that on 1 square centimeter of PD surface, 420 is the number. So we use the total charge divided by 420 microcoulomb of all the catalysts. Then we can get the ECSA of all the catalysts. The picture shows the setup of enzyme oxidation. In the setup, we dot the catalyst on glassine carbon working electrode, and we use palladium wire as counter electrode, using calomel as reference electrode. The electrolyte is potassium hydroxide, and we use this setup to perform enzyme oxidation and the durability test. In the enzyme oxidation, the forward scan peak is due to the oxidation of chemisorb enzyme, and the backward scan peak is due to the intermediates of oxidation like hydrocarbon from incomplete enzyme oxidation. This chart collected the current densities and specific max activities of AU to PD 1:1 in alloy case, all of kosher structures, and PD icosahedral. We can find in kosher case, AU to PD 1:1 is the best. Generally, the current densities and specific mass activities of AU-PD nanocatalysts are higher than that of PD icosahedral and commercial PD. In the durability test, we can find rapid current decay shows the poisoning of the catalyst. Speaking of the durability, AU enhanced the activity of PD for enzyme oxidation and excellent stability with durability, higher than that of PD icosahedral and commercial PD. To conclude this study, first, we successfully synthesized AU-PD nanocatalyst in one-step strategy. The one-step strategy has been recognized by many chemists because it can not only drop the temperature of chemical reaction, but also can control the compositions and structures well with one step. Then we control the structures by flipping the ionic switch of bromide and chloride. Thus, it is possibly applicable to the other synthetic systems. Moreover, in the enzyme oxidation, we found in kosher case, AU2PD 1:1 is the best. Therefore, we can find blending AU will improve the electrocatalytic activity. As for the durability of AU-PD nanocatalysts are higher than that of PD icosahedral and conventional PD. We want to show our appreciation and acknowledgement to the following units. During the period of this journey, we go many places and we create the impressive memories and remarkable experience of our life. We feel very grateful and we will never forget. Thank you.
ありがとうございました。それではぜひご質問などしていただければと思います。ご質問のある方、挙手をお願いします。どうぞ高校生の皆さんもよろしければご質問あれば手を挙げてください。ご質問は出ません。松坂先生も。
So at the beginning of your talk, you mentioned that a number of palladium-based bimetallic nanocrystals have been prepared so far, some of which showed some excellent catalytic activity for several chemical transformation reactions, right? So my question is, what are the characteristic feature of your palladium gold nanocrystals compared to the other systems, which include the preparative procedure or catalytic activity or nanostructure or something like that?
In our experiments, we choose palladium to combine with AU to perform this study. We don't choose palladium because the palladium is more expensive and palladium is hard to be difficult by intermediate CO.
So some other researchers may prepare the palladium gold nanocrystals, right?
Right.
So, and you also prepare the palladium gold nanocrystals.
Palladium.
So, but my question is, what is the difference between your gold palladium nanocrystals and other gold palladium nanocrystals ever known?
Our research is different from the other research because we can control our structures of catalysts with simple reactions. We use halide ion to control their structures, and it is simple. So we think it is different from the other research.
Thank you.
Thank you.
ありがとうございます。それではお時間となりましたので以上とさせていただきます。ビントンカントリーファンリャオシニアハイスクールの皆さんでした。ありがとうございました。